Hello everyone, welcome to this presentation. My name is Marilyn Van End. I'm from the Department of Material Science and Engineering at Seoul National University. I am an advanced user and developer of process simulations using FactSage microprocessing. And the goal of this video is to illustrate how to use FactSage macroprocessing to develop a simple process simulation model. And in this case, we will look at the interaction between hot metal and slag for the purpose of desulfurizing the hot metal. So I will build the simulation model step by step from the ground up. I will briefly explain the process and the approach to model it. I will draw the process flow sheet, create the Equilib files of all reactions, write and run the macrocode piece by piece, and show the commands to interact with Excel worksheets during runtime. I will also emphasize the typical errors that can be made when writing and executing the code. So this presentation is intended for experienced users of FactSage who have already watched the previous video dedicated to the syntax and concepts of macroprocessing. The main macro commands and functions will be used here, but not explained in detail. So let's look at the description of the process here. So in this process, the hot metal, who assume a mass of 100 tons, which is simplified to the FeCSI system, other impurities are neglected here, is brought in contact with a top slag, which is assumed as 5 tons here, limited to the CaO SiO2 Al2O3 system. We'll make a couple of assumptions to simplify our process. We will assume that the hot metal is well mixed, that the slag is also well mixed and in equilibrium with the solid phases, which are limited to solid oxide in the system. These solids remain in the slag at all times, so we have no reactions between the liquid metal and the solids. The process is at constant temperature, meaning that the liquid metal, slag, and solids are at the same constant temperature. There are reactions occurring at the slag-metal interface, here, between liquid slag and liquid metal only, so the solids do not take part in this reaction. And most importantly, we will consider kinetics for this chemical reaction, meaning that these three phases are not immediately at equilibrium, but move toward equilibrium at a certain rate. So FactSage will give you the equilibrium results, that is the direction and the final state of the phases. But in reality, equilibrium will take time to be established, as kinetics will affect the rate of the reactions. So we will try to simulate this with FactSage by allowing only a portion of the phases to react, instead of the entire phase at once, so that the phases move toward equilibrium, but not immediately. So let's try to illustrate this. Let's assume we have a phase of 1 ton. Only a portion of this phase, indicated by X here, will react with another portion of a phase and reach equilibrium. Here. So its composition will change and become green light here. The rest of the 1 ton has bypassed the reaction, so its composition remains the same. Then these two streams will homogenize, and we obtain a phase that has moved toward equilibrium, but has not reached equilibrium yet. In this approach, kinetics will affect the proportion of phases going into the reaction path. So if the kinetics are fast, the portion X here will be large. Thus, the entire phase here will move quickly toward equilibrium. On the other hand, if the kinetics are really slow, then the portion X here will be small, and then the entire phase will move very slowly toward equilibrium. So the key is to find the proportion or the amount of each phase that takes part in the reaction and link it to the process condition. But it's beyond the scope of this presentation. Here we will simplify these kinetic factors. Let's look at the reaction scheme for the hot metal desulfurization example. The first task is to identify the reaction zones. They are usually located at interfaces. In our simplified example, the reaction zone is at the interface between the liquid slag and the liquid metal. So to consider kinetics here, I will divide the bulk phases into reacting and non-reacting zones. In the case of the hot metal, I will define a volume or a mass of metal near the interface here that will react with part of the liquid slag within a given time. This is the hot metal reacting. The rest of the metal is far from the interface and won't be in contact with the liquid slag during that time, so it will remain unchanged. Similarly, we define a volume or mass of liquid slag near the interface that can react with part of the liquid metal within a certain time. This will be the liquid slag reacting. The rest of the liquid slag here is too far from the interface and won't have the opportunity to react within that time, so it will remain unchanged. The mass of these two reacting phases do not have to be the same. So kinetic factors within the phase, so like stirring energy or viscosity, can affect their proportions individually. So once we have defined the portion of liquid slag and hot metal reacting, we can perform the equilibrium reaction, defined here as R1. So after the reaction, these two streams will be at equilibrium and will have different composition than their respective bulk phases. The next step is to homogenize each phase separately with the products from reaction 1. So we can start with the liquid metal. In reaction 2, R2 here, the remaining unreacted hot metal is homogenized with an equilibrium reaction with the reacted hot metal from R1. It will regenerate a new homogenized hot metal phase because the phase is assumed to be well mixed. Similarly, the reacted slag from R1 is homogenized with the remaining unreacted liquid slag and solids, regenerating a new liquid slag and solid phases. That's reaction 3, R3. So this reaction scheme is what we will create with microprocessing. So essentially, 3 reactions between these 3 phases. So I will explain briefly the general procedure to build a macro simulation. This is of course only a suggestion. Some stats may be skipped or altered depending on your choice, or the order can be changed. It's up to you. The very first thing to do is to draw a flow sheet. So we already roughly sketched it in the previous slide by analyzing where the reaction occurs, which phases are involved, and what steps are done. So this is an important step as it will greatly help when creating the Equilib files for each reaction. The reactants and products will be easily identified with the flow sheet. The second step is to prepare the Excel file for the input data. It does not have to be finalized at that stage, but the main input data should be identified and arranged in a worksheet so that the cell addresses are known and can be used when writing the macro code. The third step is to create the Equilib file for the initialization stage and writing the corresponding macro commands in the macro file. The objective here is to have the macroprocessor initialize the streams with the input data entered in the Excel worksheet. So here I will build the macro code piece by piece and test it regularly to identify errors that would not be caught by the macroprocessor and to make sure that it does what I want. Once the initialization stage is written and tested, we can create the Equilib files for the core of the process and write the corresponding code in the macro file. Again, it's recommended to test the code regularly. And lastly, we will organize the Excel file to print out the results and write the corresponding code in the macro file. So let's draw the flow sheet. I will go to PowerPoint here, another PowerPoint, to draw it from the ground up on a slide. Okay, so let's try this. So I have copied here the scheme, the process scheme, so it will be easier to remember the reactions. So we have 3 phases in the system that will be represented by streams in the macro code. So we have the hot metal phase, the liquid slag, and the solids. So these are the 3 streams that we have to initialize and for which we have to define the initial amount, composition, and temperature in the Excel worksheet. So this is our starting point for the process. In the first reaction, if we look back at our scheme here, part of the hot metal, let's write it Y, so we take part of the hot metal. It can be a fraction or an absolute value. Here we're going to use a fraction. will react with part of the liquid slag reacting. And let's write the amount here, Y. Okay, so we have a certain fraction here, called X, that will react with part of the hot metal. Then we have to identify the possible reaction products of that reaction. So we will include, of course, a liquid metal. Okay, so we have a reacted hot metal, which is going to be different from the bulk hot metal. And we are going to make a new liquid slag, which is also going to be different from the bulk liquid slag. And the last one is the solids, reacted solids. Because of the change in the liquid slag composition following the reaction, the solids might actually precipitate out of the liquid slag. So we need to include these possible solids that will form in this reaction. So this is reaction 1, and it's completed. We have done this part. In reaction 2, here, let's look at our scheme. The hot metal is homogenized. So we take the remaining hot metal here. So we have Y that goes here. So there will be 100 minus Y% going into the second reaction, the remaining unused hot metal. And then we homogenize it with the reacted hot metal from R1. So we take the reacted hot metal from here, all of it, and then we put it in the second reaction. From this reaction, we make a new hot metal or bulk hot metal stream, okay, here. That will replace the bulk hot metal at the next time step, and R2 is completed. In reaction 3, the slag and the solids are homogenized with the reaction product of R1. So we take the remaining bulk liquid slag here, so we add X% going there, so we'll have 100 minus X% going into reaction 3. Then the bulk solids, it's all of them because these solids cannot react in R1, so they will go directly there to be homogenized with the liquid slag. And we homogenize them with the reacted liquid slag, all of it, going back to this reaction 3. And the reacted solids will go also there. So we homogenize together all these 4 phases, and then we obtain a new liquid slag and a new solids. And these liquid slag and new solids will replace basically the bulk liquid slag and the bulk solids at the next time step. So this is reaction 3. So this flow sheet is repeated a certain number of times, which is the duration of the process, and we would like to follow the evolution of the phases with time, for example, to see how fast the sulfur is removed from the hot metal. So the next step in the procedure is to prepare the Excel file and the worksheet. So if I go back here, so we have this flow sheet, we draw it together. So the second step here is to prepare the Excel file with the input data. The idea here is that all process inputs and conditions should be stored in the Excel file, so that once the macro code is written, you don't have to touch the code anymore. If you want to change the process conditions, such as the initial composition of the hot metal, or the temperature, or the duration of the process, you just change the values in the Excel file and run the macro processing simulation without changing anything in the code. So I will open Excel now, make a new empty sheet, a blank workbook here. And I will name that worksheet inputs. You can name it whatever you like, it doesn't matter. Here I prefer to give some meaningful names. So in the worksheet, I will first create the data for the hot metal. So I'll just try to make it nice and understandable. So I will put some headers there, hot metal composition, and weight %, sorry. And then I enter the elements. So the elements in our system, if I go back to our little system, we had iron, carbon, silicon, and sulfur as a starting composition. Okay. We also need to define the total amounts. So I will give the value here. total amounts in ton or kilograms, 2. And here I will enter the actual value. So here we'll assume that we have 4% carbon, 0.4 weight% silicon, and 0.03 sulfur. Then I need to define what is the iron, so usually it's the balance. So I will basically calculate the balance here, 100 minus the sum of the other elements. So it's B3, 2, and D3. Okay, and then I will get basically the weight% of iron and the total amounts here, which is at the beginning 100. Okay, let's try to make this centered and merge these to be nice and well centered. And then we do the same for the slag composition. So again, slag composition in weight%. And then we have our elements, so CaO, SiO2, and Al2O3. And I also have to define what is the total amounts in ton for this case. We assume 5 tons. And the composition we're going to work with is 60 weight% CaO, 25 weight% silica, and 15 weight% aluminum. I can again make that nice and beautiful, merge this, so everything looks good. So then we have the process conditions, namely the process temperature. So let's put it there. Temperature. It's going to be in degrees C. Okay, which is 1400 degrees in our case. And the process duration, so meaning how many times we will repeat the flow sheet that we just created. So this is the process duration. Let's put it minutes, for example, and here we'll assume it's about 10 minutes. Okay, make this nice and written. And then we need also to put the kinetic factors. So it means, you know, this X and Y that we defined here to know how much hot metal and how much slag is going to react. And this is going to be a percentage. So this is hot metal reacting. So in our flow sheet that was Y. And this is the slag metal, liquid slag, sorry, no, not slag, liquid slag reacting. So this is X in our worksheet. And then we're going to define as 20% and 30%. So these are just random numbers, of course. You can change whatever you like, and then we put the units to make sure that we remember what it was. And I will just put this a little bit down, just to make it, let it matching everything. So here, it is a constant here for the hot metal reacting and the slag metal reacting. You can enter a value as a fraction or like absolute value. Here we're going to work with fraction. And it's a constant value, but in other more complex process, you can make it change with process conditions. But in this case, it will remain constant. So I have created my input worksheet. Of course, I can add on things later on if I feel like I've forgotten something. And now I'm going to save it. So I'm going to create a specific folder on my C drive. So I'm going to go to my C drive, and I'm going to create a new folder to make sure I'm not. And I'm going to name it Workshop DeS, the folder where I'm going to keep all the Equilib files and Excel files and so on together. And then this is going to be my, for example, DeS example Excel workbook. So it's going to be an XLSX file in this case. And I'm going to save it. And it's saved. So we have finished with our creation of the flow sheet of the Excel file. So now we are ready for the third step. We need to create the Equilib files to initialize the 3 streams. So we need to specify in this Equilib files what are the reactants and the product phases. So we don't have to specify quantities in the Equilib file. So we will do that in the macro code. Then we can write the macro code to create the streams with the actual input data stored in the Excel worksheets that we just created. Okay, so this is the step number 3. So we have to go to Equilib module of FactSage. So I will open Equilib. We first need to change the My Files directory. So I have to change it, the My Files directory. So you go to Files, Directory, and then change My Files directory here. And then you navigate on your C drive to find the folder where you created the Excel file. So here I named it Workshop DeS. So I have to double click on it to make sure that the little folder image here is actually open. Okay. And then once I'm done, of course, there is nothing inside yet. I haven't created anything. And then I click OK. Again, here, no Equilib files are created, so it's totally normal that it's empty. Let's just close this. And then I will start making the hot metal initialization. So start with the hot metal. So we make sure we have an empty page. If you don't, you press this to make a new reaction. And then we enter the elements that we need. An important thing here is to follow the same order as you have entered the element inside the Excel. So we'll enter this. We see here for the hot metal, we have 4 elements. So I'll make 4 entries. And then I'll just enter the species. So here the elements: iron, carbon, silicon, and sulfur. That's very important to follow the order there, because it's going to help us when we write the macro code. We don't need to change the quantities as at this stage, so it can stay at 1, because anyway the macro processor will change the values with whatever you wrote inside the Excel worksheet. So let's check that the units are correct and modify them if we need. So the temperature should be in degrees C in Celsius, the pressure should be in ATM, and the quantity should be in grams here. So we're going to look to work with grams, although we actually have tons in there. So we have to remember, if we look at energy or volumes, that we have a factor 10 power 6 between our units and the units set in FactSage. So our units are okay, so now we have to check the database. So we go to the data search menu to change the database. I will clear them all, and here we'll select the FT miscellaneous database here, FT miscellaneous, FT misc, to get the FELQ solution for the hot metal. Okay, so once we have this, you can say OK. There's a little particularity that I will make here to basically normalize and get all the possible elements in the hot metal from the start. So that will make the printing of the results easier later on. So as you know, once the metal and the slag will have reacted, some elements from the slag that are not yet in the metal will be transferred to some extent to the metal. So we have to check which elements from the slag would eventually get into the metal as well. So we compare basically the both system, and we see that, for example, calcium, aluminum, and oxygen are not yet defined in the hot metal and could be transferred to the hot metal during the process. So when the slag basically gets to react with this. So I will add them as reactants. So calcium, aluminum, and oxygen. So calcium, aluminum, and oxygen. It's very important here is that we have to put their mass at 0, okay? Because I don't want to have calcium, aluminum, or oxygen at the beginning, but I want them to appear inside my phase selection. So I have to put their mass at 0 so that they are not like physically or materially as present inside the phases. But they will not have any mass. So also we make sure that the initial conditions is not checked. because we don't need to have delta values right now. We can then press next to go to the phase selection. Okay, we select only the FELQ solution in this case. We're not interested in having any solids or other phases. So one phase only. The final conditions here should also be set to perform calculations at the given temperature. So this field should have something, and the pressure should be 1 atm, and the last field here must be empty. Okay, so then we save the Equilib file in the directory C workshop DeS. So I go to File, Save As. Okay, because I changed my files directory, I will directly be inside this workshop DeS. And then I will name it hot metal init. Hot metal init, sorry. I don't have to add the .equi because the FactSage will add it for me. So hot metal init. Okay, I can make a comment. So for example, initialization of the hot metal. You don't have to, it's just for yourself to remember what that Equilib file was doing, but you can leave it empty too. Okay, so the Equilib file for the hot metal initialization is done. So now we have to do the same for the slag and the solids. So we have to make an empty system. Okay, click clear, say yes, whatever. And we enter the components of the slag following again the same order as in the Excel worksheet. Okay, so we have three components. We have CaO, SiO2, and Al2O3. Okay, so again, we don't have to change the quantity at this stage because the microprocessor anyway will reset the values during the simulation, so we don't have to worry about them right now. The units are still correct. Okay, so the units we haven't changed anything, so the units should be still fine. And then we go to data search. We can clear our previous selection to make sure we don't have several databases, and then we select the FT oxide database. So this will give us the liquid slag and also the oxide species, like pure compounds, solid pure compounds. Okay, we will also do the same by adding the elements that are not yet in the slag and could be transferred from the hot metal. So if we compare again the system between the hot metal and the slag, we can see that the iron and sulfur could be transferred to some extent to the slag. So when there is a reaction between the hot metal and the slag, some of the iron and some of the sulfur will be transferred here. So to have these elements already present in the phase and the species selection, we will add them here. So we have two missing elements, which is iron and sulfur. And then we make their mass 0, so to make sure that there's actually no amount coming in to the initialization. This is just to make the phases containing iron and sulfur in our phase selection appear right from the beginning. We see also that we have carbon, but in this case, we don't need to add it because FT oxide does not contain any carbon containing species, so it will not come in the phase selection anyway. So we don't need to add them. So we add these two elements, iron and sulfur, with the 0 mass to make sure that the phase and species selection will list them right from the beginning. Then we click next to select the product phases. We select all pure solids. Okay, there is only one solution or database here, so there are no possible duplicates in this case, so we don't need to check the list. And the solution slag A, here if you click on it, automatically it will be set as immiscible with this I option checked. So, and then that's it. So we have pure solids and the liquid slag, and we are okay with this. And then we can see here that we're basically initializing the two streams at once. So the solid stream and the liquid slag stream. Let's check the final conditions. We need a fixed temperature and a pressure of atm, and the last field must be empty. Then we can save this Equilib file as, for example, slag init in our folder. Okay, so we are still in the C workshop DeS. Okay, and then we're not going to name it slag init, of course. We're going to name it slag init, and don't have to put the .equi here. And we save it there. You can also put a comment to remember what it is about. Initialization of the slag and solids. Okay, and that's it. So we are ready with the Equilib files. So now we can start writing the macro code to tell the macro processor to read the values from Excel, open these Equilib files that we just created, change the reactants amounts and calculation conditions, perform the calculation, and then create the stream files for us. So I will open Notepad++. I usually work with that text editor. Create an empty page if you don't have it here. You can use any other text editor if you don't have Notepad++, like Notepad or anything else. And then we can start writing the commands to do so. I will also open the summary sheet that should be in your package, where basically all the syntax of the main macro processing commands are basically kind of summarized here. So for general commands, variables, functions, step and loop, set and save, and OLE commands, and also macro thermochemical variables here. Okay, so you have everything listed here with a small summary of what it does.